In this video, we're going to take a look at ozone depletion and recovery. So ozone is a very beneficial gas. We want it in the stratosphere in a fairly high concentration. It actually shields us from harmful UV radiation from the sun. But we consider ozone in our troposphere a pollutant, so that's kind of where the confusion lies. In the 1980s, scientists discovered that human-made airborne chemicals called ozone-depleting substances were causing the degradation of the ozone layer. So the ozone layer in the stratosphere, we want to stay intact. We do not want to cause airborne chemicals to deplete it. So what are these ozone-depleting substances that we were creating? So one was halocarbons. So halo, you may recognize the prefix of here is halogens. So atoms of chlorine, fluorine, bromine, that's not all the halogens, but that's the ones that were making halocarbons, combining from hydrocarbons and then replacing the hydrogen atoms, which is something that they do fairly readily because we know the halogens are very reactive. And then specifically chlorofluorocarbons, or CFCs, you may have heard of, were produced in the 1970s for use in refrigerators, fire extinguishers, propellants for spray cans, and cleaners for electronics. Not because they were toxic, but because they were just very versatile and cost efficient to put into these substances. It was later that we discovered chlorofluorocarbons are depleting the ozone layer, and that exposes us to UV light from the sun, which can cause cancer and all sorts of other degradation to like plant and animal life. So CFCs are very non-reactive, and they were assumed to be safe for the environment. So chlorine is very reactive, but when it's in compound, it can be very stable. So in the stratosphere, the CFCs are broken down by the UV radiation, and UV radiation and other types of heat, they often cause chemical reactions to occur more readily because they increase the energy of collisions. And then chlorine and carbon atoms split many ozone molecules. So let's take a look at the cycle here. So we got aerosol cans, refrigerants, air conditioning units here. We got the CFCs that were thought to be stable, but when we get them into the stratosphere, way up above our troposphere, they break apart ozone into oxygen, and then they form chlorine monoxide, and then the ozone starts to be depleted at an alarming rate. So we could actually record this depletion each year. In 1985, researchers detected that an area of thin ozone concentration called the ozone hole was actually forming every spring over Antarctica in the South Pole. High altitude polar stratospheric clouds containing nitric acid were breaking CFCs down into chlorine, which was then being released in the spring when the sun broke up the clouds, when heating, more direct sunlight happened. Scientists were concerned that elevated UV levels could promote skin cancer and damage plant life. So this has actually led to, in 1987, an international treaty that has been one of the most successful environmental treaties ever agreed upon, and it's called the Montreal Protocol. So countries agreed to cut CFC production out by half in 1998. Additional agreements were passed, adding 2 more halocarbons to the restricted list. Now, the part of the boost for this is that they were able to find other types of refrigerants and products that could be replace CFCs fairly affordably. And that was what was the main problem in the lead industry. Lead was so readily available and cheap and so good for so many substances that they didn't have a cheap alternative, and so industry fought back big time. So part of it was international responsibility, but part of it was that the market could transition easily. So we went from the ozone destroying potential from all substances, parts per billion, effective stratospheric chlorine, to almost 0 emissions for Beijing and Copenhagen. Without our protocol, it was projected that we would have exponentially grown and caused permanent damage to our ozone layer. So phasing out and replacing these chemicals has stabilized the ozone layer, and it's actually expected to fully recover sometime the year after 2016. So it's a slow process of recovery, but it is a reversible process. And this is now the model for solving global environmental problems. So millions of square models, and we've got like this cyclical change, and we're going to stabilize in the coming years. So in the next video, we're going to talk about acid deposition or acid rain.